Hello, this is Dr. Shefali from Walchand College of Engineering, Sangli, India. I would like to discuss few problems on mathematical induction. This is the part 1 of the tutorial. Of course, I would like to give some acknowledgement of the author, John Martin. The book which I referred as Introduction to the Languages and Theory of Computation, the third and the fourth edition, which are important to prepare and solve the examples for me. Coming to the first example, I would like to say that suppose the question is given for mathematical induction that prove for every n which is greater than or equal to 0, if some series is given to you, let the series is given in the form where a summation of I square, where I range from 1 to n, is equal to n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6. If this is the series, as we know that the fact is that mathematical induction is for proving the theorems. This is not for the discovering the theorem, but it is for the proving the theorem. And definitely that proof is for the positive numbers. It is not applicable for the negative numbers. Now for every case, possibly we need to start from the base case, for which I'll say that suppose this equation is considered as the predicate. For this predicate P of 0, that means I want to just put the value of n as the 0, and I want to check that for the base condition, whether the left hand side of the equation is satisfied to the right hand side of the equation. So here definitely, if we try to find out the left hand side, is though it is the range is given from 1 to n, I square, the value of I, if it is taken as the 0, then the left hand side comes as the 0, so as the right hand side 0, because it is multiplication by 0. So for the base condition, it is true. We'll move further for the next step, that is the hypothesis step or the induction step, for which we can assume for the predicate involving integer k, where k is necessarily greater than or equal to your base condition, and that base condition is 0. So we'll write it down as the k is greater than or equal to 0, and we have to rewrite the series as if it is the summation of y 1 to k, okay, the range is given, and the I square. So ultimately we have to have certain assumption that the right hand side is true. That is the hypothesis. With this hypothesis, we have to move further. So we have to write it down in the form, which is the form given on the right hand side. Continuing further, what exactly we want to prove? We want to prove, as I said, that it's an iterative process. So from 0 to the next integer, from the next integer to the very next integer, ultimately for in between some kth integer, wherever we assume that it's a true, and if we are able to prove for the further next integer, that means it is say successive process, then ultimately what hypothesis we have made, we can assume that the given hypothesis is the correct one, and we can prove or we can claim that both the sides are equal throughout for every possible integer which is greater than or equal to 0. So we can rewrite the predicate P involving integer k plus 1, where we assume or where we expect that the series left hand side should become in that way, and the right hand side where n can get replaced by k plus 1. So n we have replaced here k plus 1. Then n plus 1 is coming as the k plus 1 plus 1, and then twice of n, where n is replaced again by k plus 1. So we expect that this particular series should be equal to the right hand side series. So how to start this one? Definitely there is some systematic approach to go for having the solutions, and always you need to start from your hypothesis. Just this is the one of the clue, one of the hint for every one of you, that always we need to start from the induction hypothesis. So what my hypothesis is saying? My hypothesis is saying that if the particular requirement is there, suppose this is the requirement, where the range is from 1 to k plus 1, that requirement should get satisfied by the already proved series from 1 to k, okay, plus the added term, and the added term is k plus 1 bracket square. Okay, so if this is the added term, Then from the earlier proof, this was the earlier proof. I can say that the earlier condition was given here. Okay, I just want to use some pen here. I can say that the earlier situation where the say k plus 1 price of k divided by 6, which is already proved with the say method or with the hypothesis here, and then you are going to add upon the next element. So when the next element is to be added, then we can say that it can come out, or rather we can have certain arrangement, rearrangement rather, so that whatever is the right hand side you are getting right now, that arrangement you have to rearrange into the required form. So looking towards the required form, we can say that, okay, we can just take out k plus 1 out of the particular bracket, and then we can rearrange the bracket in that sense. Definitely, you will be agreeing upon for the arrangement of those what we have gone for. And with this arrangement, now if the next step is there, then with the next step, I can say that, okay, the k plus 1 is taken out of this one, where 2k multiplied by k can be taken out as the 2k square plus, okay, you can go for the 7 of k plus 6 and divided by 6. So entire term is going to have as the division by 6. So ultimately this forms, if we try to decompose this particular bracket, 2k square plus 7k plus 6 can be divided as if it is a k plus 2 and 2k plus 3, because this is the requirement what we expect on the right hand side with my cursor here. And ultimately this can be rewritten as in a form which is the exact requirement what we expect for the predicate involving integer k plus 1. Just check it out that the value or the writing of the variable k slightly differ here and with this particular equational part, because this equational part is written in the math editor, and this is the say your editor what you are saying, that is your normal. So slightly the font may change, but ultimately the meaning is the same one. Okay, so with this idea, I can say that we can move further. The second example starts with one of the series. Say the series is of real numbers, where the real numbers may be formed in a way involving some numbers a0, a1 up to an. So we can have here n is greater than or equal to 1. And it is expected that we have to prove that summation of 1 to n of the elements where the ai minus the preceding number, that is a I minus 1, should be equal to an minus a0. That is the extreme right end of the set and the extreme left end of the set. So in that way, if we start proving here, as the conventional idea, we'll start with the basis. Now it is clearly given that n is greater than or equal to 1. So it means that we need to move for, or we need to start from the first element, which is 1. So base condition is 1. So predicate involving 1, where a1 is the value for n we can choose. For the LHS, we expect that it's a a1 minus a0, so as the RHS. So I can write it down here as the LHS and the RHS, which is very clear. Now we'll move for the next step, which is the induction hypothesis, which is required for the predicate involving integer k, where necessarily the k is greater than or equal to the base value. And now in this particular example, the base value is 1. So we can expect, or we can write it down, that summation from say k1 to whatever, we can write it down in the right hand form, where the ak minus a0, which is the hypothesis, which is the induction step. Now what we want to prove, if we are clear with all those steps, because as I have given the steps in a very clear form, ultimately the clarity gives us the way in what way we should proceed further. So we want to prove that predicate involving k plus 1 as the step, where the RHS is to be expected that it should be a k plus 1, that is the step, minus the basic element, which is the a0. So in that way, if we want to start, of course, we have to start from the hypothesis, which is the induction hypothesis already proved for your, say, kth element proof. That means it is assumed. We can say that's why it is called as the hypothesis. So whatever the series is given in a question, that series for the element k plus 1 can be rewritten in that way, which is equivalent to the earlier series, and the earlier series is having the scope from 1 to k plus one more element for the k1 plus, that is the element where, yeah, that element you can add upon. So the kth series, up to the kth series, the series can be involved as it is, plus one more term is there, and ultimately that term can be obtained with the idea where 1 to k, for those elements, the right hand side which is assumed is equal to ak minus a0 plus one more term which you want to add can be given in this form. So I can say that that particular term which is going to have the just the rearrangement, and the rearrangement can be formed in a way where the ak minus a0, which is the earlier term, fine, and the new term what you want to involve, okay, this is the term, just rewrite those terms. That means ak plus 1 and the ak minus 1 and ak plus 1. Okay, you can write it down with this minus, and ultimately the rearrangement can be given in a form, and that form is equal to a k plus 1 minus a0. So that is the idea. With this idea, where the expectation what you had earlier, that expectation can be fulfilled. Okay, so with this idea, I think I need to move for the next example. The next example expects that I have to prove for every n which is greater than or equal to 1. Again, the summation which is ranging from 1 to n, where 1 upon I multiplied by I plus 1 term should be equal to n upon n plus 1 term. So how to write it down again? Of course, the hint is given that for the series which is greater than or equal to 1, so the predicate involves the base number which is 1. So LHS is equal to, say, I can say that 1 upon 1 plus 1, so it is equal to 1/2. So as your RHS, so for base condition 1, the series is proved. Okay, so we can move further for the induction hypothesis. So we can assume again that for some k value which is of course greater than or equal to your base value, the RHS is equal to k upon k plus 1. Now we have to move further for the induction step as declared in the previous example. So as we'll assume that for the predicate involving k plus 1 as the integer, the right hand side is expected to be, just go for the replacement of the term. Instead of the k, it will be k plus 1, and the k is replaced by again by the k plus 1 can be carried out here. How to start? Again, start with your hypothesis with a thumb rule, whichever the rule what we have discussed. That will give you clarity that, okay, from where you need to start, you need to always start from your hypothesis, and you need to end always to your expectation of the right hand side, or whatever the rearrangement of your left hand side and the right hand side. The series what we discussed earlier and right now also, these series are involving equality. So that equality we need to maintain. So how that equality is to be maintained? So for your series ranging from 1 to k plus 1 is equal to nothing but it is the summation of the series which is ranging from 1 to k plus one more term. That one more term we have added as the same task what we carried out for the previous example. That can be equivalent to, okay, the summation from 1 to k is nothing but k upon k plus 1, which is already declared in the hypothesis, plus the additional term you can add upon here. That additional term where you want to simplify the term, just try to find the denominator as the same one, which is the k plus 1 and the k plus 2 multiplication by this one. So obviously the first term is required to have the multiplication of the k plus 1 at the numerator side, so that it will so multiplication by both the numbers, it will give you the, say, equivalent number. So multiplied by k plus 1 to the numerator as well as to the denominator makes say same result. So ultimately your series can be formed in this particular rearrangement. That rearrangement can be described. So you can say that if you go for expansion of this one, it is equal to k square plus twice of k, okay, plus 1. So that is nothing but it's a k plus 1 bracket square. So once you come to that particular solution, every time your rearrangement, your solution should be in a sense that you have to look to your particular right hand side. What exactly is the arrangement expected? According to that, you have to rearrange your formula. Okay, fine. So that ultimately will go for having the result, and that result is the exact result what we expect for the arrangement for the k plus 1 as the predicate. So if we are able to prove this, if we are able to show that left hand side is equal to the right hand side, then we have proved the particular series, and that proof is with the method, and that method is your mathematical induction. Coming to the next example. Suppose for the range greater than or equal to 0, n is the integer, we have to prove that the given series where the right hand side is given in terms of your factorial. So how to come with this particular series? Obviously, if we go for the involvement of the 0 is the base number. Normally, such type of the examples say that we can start from the series 1 because n is expected to be the natural number, integer number. Normally, the range is from 1 to infinity. But if specifically mentioned for n is greater than or equal to 0, then definitely we can take this particular base as the 0. And this particular equation says that just you can compare with this method, and you can say that, okay, fine, it is equal to having left hand side is equal to your right hand side, and which is nothing but your 1 itself. So again, go for the hypothesis P of k. So for k, you need to mention this. There is, okay, this particular mentioning is very compulsory. So k, which is greater than or equal to your base value, which you have considered for the P of 0, RHS comes as the, okay, you can make the hypothesis which is equal to k plus 1 factorial. Now, what exactly you want to prove? You want to prove that, fine, the statement is to be shown for the induction step is that predicate k plus 1 should go for, just replace the term n by k plus 1 plus 1 factorial. That is nothing but is your k plus 1 factorial. So that is k plus 2 factorial rather. Okay. So in that way, whenever you are going for the proof purpose, you will always start from the induction hypothesis. Hypothesis says that, okay, you have already given, say, your term. So the predicate P k plus 1 is equal to involving predicate k plus you are having one more term here according to your given series, and that term you need to have the rearrangement. So just try to expand this term predicate involving k, which is equal to some value, and that value is already given, which is the k plus 1 factorial. Now just go for adding this replacement here plus k plus 1 multiplied by k plus 1 factorial. So just have your rearrangement. It is equal to, what you can say that you can just take out k plus 1 factorial out of your bracket and then plus 1 term and k plus 1 as one of the one more term. So you are having the multiplication. So in a sense, it will come upon as the k plus 1 is equal to k plus 2. So k plus 2 multiplied by k plus 1 factorial is nothing but k plus 2 factorial. So in that way, we have again proved the fourth example. In this line, if we are trying to move for the further examples, the next example I would like to say, now the example here comes with some relational operator. Earlier, we have gone for some equality operator. So for every n greater than or equal to 2, just check it out that some base condition is given here. Some hint is already given. So my series starts from 2 to 2, the range is given. We have to prove the right hand side here. So for the base condition where the predicate involving 2 as the base condition, it is given. So we have to follow this particular base condition. And with the conventional method, the earlier method, we can prove the base condition, then we can have the induction hypothesis, and directly we can move for the predicate involving k plus 1. So using the same fashion, I can omit few of the statements and I can directly move, say, for the k plus 1 as the range, that is from range from 2 to k plus 1, where the left hand side is given 1 plus this series should be equal to 1 plus series involving the series from 2 to k, okay, plus k plus 1 position factor, and that factor is 1 upon square root of k plus 1. So if this is the example, how to move further? The same idea is that, okay, whatever is the say earlier expansion we carried out, we said that 1 plus series ranging from 2 to k, this particular series, when we want to just use the series, we can say that this particular series, okay, this particular series is greater than root k, because already this is declared here. And then we have to make plus, that plus is, okay, 1 upon root k plus 1. So instead, when it is equal to, the equality sign was maintained here, but this particular term, okay, this particular term is greater than root k. So we have to maintain this particular relation. So with this relation, if I move further, I can say that I can use the very next term, and the very next term, that is the root k plus 1 upon root k plus 1. This term is equal to, now I just want to keep this greater than relation afterwards for the further one, but now root k plus 1 upon k plus 1 square root, that term can be made somewhat simpler, where the root under root of k plus 1 is multiplied to the root k, and you can take the common denominator, that is the under root of k plus 1. So you are having this particular red term is equal to that red term itself. But now we would like to say that, fine, this term, whatever the term we observed here, that term should be greater than root k plus root k plus 1. Why we did this? Because here is the additional 1, that is the plus 1 is there. So we have just not used that plus 1 here. So obviously this term should be greater than this green term. And what that green term says, that is equal to, you can go for certain simplification of this term. So once you do the simplification, I can maintain the relation, I can continue the relation further, that I can have here, okay, which is greater than k plus 1 under root of root, okay, k plus 1. So why I did this? Why I dared to do this? Because as I say that root k is there, and root k is always greater than 1. So instead of the root k, I used here the term 1. So k plus root k, I used here the term k plus 1, and compared to this term, this k plus 1 under root of, say, square root of k plus 1 is greater than, because always root k is greater than 1, because we assume k which is greater than or equal to 2, because the series is true for this condition. So for any k which is greater than or equal to 2, always your root k is greater than 1, and hence we can maintain this particular relation. And with this relation, this is nothing but equal to, or it is greater than root k of say under root of k plus 1 as the term, which is the requirement. And I think we have proved the particular series. With this particular example, I would like to go for one more example again, a slightly different category, which is the divisible condition. So for n greater than or equal to 0, the term is given n bracket n square plus 5, it should be divisible by 6. We have to prove this. For the proof purpose, the basis compulsorily should be taken for the 0, and 0, of course, even though you go for the 0 multiplied by 0 square plus 5, the ultimate value is 0. 0 is divisible by 5, so predicate 0 is proved. For the predicate involving k integer, we'll assume that, okay, it is divisible by 6. We'll assume that it is divisible by 6. We are not interested in the say what is the division. So we can assume that whatever the division is there, let the division is integer value, some integer value. Okay, but I think for this example, it is not required. So with some, say, ordinary induction, what we are using, we can say that, okay, if we are trying to rewrite the equation for the predicate k plus 1, so n can be replaced here with the k plus 1, n square plus 1 can be replaced here, k plus 1 bracket square plus 5, and that is equal to, if you go for here, k plus 1 cube plus 5 k plus 1. You have just rearranged the terms. Now rearranging, or rather the expanding k plus 1 bracket cube, okay, I can say that I can come upon with this particular equation. Why? Because I can take some reference of the cube of a particular bracket. So I can say that a plus b bracket cube, if it is there, it is equal to a cube plus b cube plus 3a square b plus 3ab square. In our case, a is k and b is 1. So just looking to this particular equation and just adopting the cube equation, we can have the expansion of the bracket, and that expansion of a bracket plus the remaining term 5k plus 1 you can have here. So just rearranging the term, I can say that it is equal to k cube plus 3k square plus 8k plus 6. Now looking to what is the requirement, that is we have to prove for the k plus 1 term which should also be divisible by 6. So it can be rewritten as, this particular equation can be rewritten in the form. The form can be given here, okay, that ultimately I can have here the form. I'm just looking towards what exactly I have and where I need to move. So this can be rewritten as k in the bracket k square plus 5, okay, which is actually proved earlier, and plus one more term is there. So ultimately this is the entire term what we are expecting. But now I can say that the term which is given in the red color, okay, this is the first term, that is divisible by 5, divisible by 6, okay, not by 5, because induction hypothesis is saying so. So we have to accept this one. And now the other term, okay, which is the green term, where the two successive elements are there, k and k plus 1. When we are having two successive elements, either k or k plus 1 will be the even number, okay, because these are two successive numbers and these are the integer values. Of course, the step size is 1. So whenever one of the element, either k or k plus 1 is even, then definitely the multiplication is even, because even multiplied by even is equal to even. Even multiplied by odd is also equal to even. So once this term is even, then I can say that this multiplication is even, and this even number multiplied by say 3, of course it is divisible by 6. So this first term is multiplied by 3, any numbers. So first even number is 2, okay, 2 multiplied by 3 is equal to 6. The second even number is 4, 4 multiplied by 3 is equal to, which is divisible by 6. Also, you can find it out. So both the terms are divisible by 6, which is the requirement, what we want to prove. So hence, I can say that the proof is given. Then I would like to say one more example, which is related to your relational operator again, and that may strengthen the idea of the proving of the mathematical equations. So I can say that there is some term b raised to n minus a raised to n, and necessarily the range of your n is given, and the range of a and b are also given. That is, the relation of a and b is also given. When I say b minus a, so I should say that a is not equal to b, but b is of course greater than a. Okay, so that is the relation, and it should be divisible by b minus a. So in that way, whenever the first term is there, the first term involving 1, predicate involving 1, gives me very clear-cut option that it is divisible by b minus a. Predicate involving k, okay, where the k is necessarily greater than or equal to 1, I can say that, okay, b minus k, b raised to k minus a raised to k is divisible by b minus a. We can assume. With this assumption, for the induction step, again, we can rewrite the equation with the given condition also, that b raised to k plus 1 minus a raised to k plus 1 should also be divisible by b minus a. So we'll just try to rewrite, and we can take the help of the hypothesis. So this term, this is the k plus 1 term, can be written in the form of hypothesis, and that hypothesis will allow me to have an equation, okay, b multiplied by b raised to k, a multiplied by a raised to k, okay, that I can just rearrange, or I can just have the addition and the subtraction. So I can just go for the effective addition and the subtraction of the term which is required for me. So I'll just maintain the equation, and these two terms are added. That means one is the positive term and one is the negative term, and I can rearrange the given equation. So b multiplied by b raised to k minus a multiplied by b raised to k. So I can take out the b raised to k and the b raised to k, which is out of the, say, bracket, and I can have here the b minus a as the relation. Okay, I can just put down in this particular bracket, And here the next term is there where I can take out a out of the bracket, and b raised to k minus a raised to k I can rewrite again. So this particular, the earlier equation, this particular equation can be written down in this other format. Now b raised to k minus a raised to k, obviously this is divisible, which what we have said in the say induction step. And now we have to prove for this one again, b minus a multiplied by b raised to k. This is also divisible by b minus k. So I can say that, okay, fine, with this particular case I can prove, or I can say that you can rewrite, or you can use here that the next step, which is the green color bracket is there, obviously divisible, and of course with the induction hypothesis this is also divisible. So hence whichever is the requirement, that requirement we have proved. So in that way I have given you some of the examples for the mathematical inductions. In the next part I would like to extend this particular application to your language theory, and how to solve those examples with the mathematical inductions we can say. Till then, if any question, you can contact me, and I can say that with this one, I can pause my recording, I can stop my recording.